Hello everyone, this is Doug Young, and in this video we're going to talk about electrolytes, kind of what they are and how to identify strong, weak, and non-electrolytes. Now you may have heard electrolytes before out in the everyday world, probably in a commercial trying to sell you some sports drink like Powerade, Gatorade, something like that. You might hear something like it replenishes your electrolytes. And what they're talking about is they're trying to sell you a drink that's mostly sugar water, but they're saying that it improves hydration because it has certain electrolytes in them. And these electrolytes are ions that you lose in sweat. You also lose them in urine and other body fluids, but largely sweat if you're doing a lot of heavy sports, right? And the idea is that you want to replace those so that your nervous system still works as well as it could in an optimal way, and so that you don't get dehydrated. And so we're going to come back and talk more specifically about what are the ions and stuff that we're talking about if you're looking at something like Gatorade. What are the electrolytes, and how might those sort of benefit you? Now, in chemistry, when we say electrolytes, we're talking about something completely different. We're not talking about something to kind of like help rehydrate you. We're talking about something that helps impart conductivity to a solution. And so water is a very poor conductor of electricity. Most people think, right, it's a misconception that water is very conductive, because you see sort of things where people get electrocuted in water, and you don't want to touch a light switch if you have wet hands and those sorts of things. But that's because the water that we're mostly around is really impure and has a lot of electrolytes in it. If you took pure distilled water, really pure clean water, it's not a good conductor of electricity. It's very hard for electrons to move through it or charged particles to move through it. And so what we do is that we add electrons, and that's going to greatly increase the conductivity of water. And again, things like tap water for us, those have electrolytes in them. You might know like there's calcium in them and chloride in them, stuff like that. So in chemistry, when we say electrolyte, we're talking about a compound that produces ions when dissolved in water. And that the big thing here is that they need to be ions, right? So it's not anything that dissolves in water. It's something that produces ions when it's dissolved in water. They can be positive, they can be negative, +1, +2, -3, whatever it is. It just needs to produce ions when it's dissolved in water. And because the idea here is if you have something like ethanol, and I'll draw out ethanol real quick. If you have something like ethanol, which is CH3CH2OH, ethanol is a covalent compound, right? All of these things are nonmetals, or in other words, they all have a very small difference in electronegativity to one another, right? They're all polar or nonpolar bonds. This is a covalent molecule, right? The thing here is that there are no ions formed when this gets dissolved, right? It does not dissociate in any way. It's not an acid, it's not an ionic compound. So there's no ions, which is why this little diagram says no conductivity. And what we see with this no conductivity is that the light bulb here is not being lit up, right? It's dim. So what that's supposed to show you is that there's no electricity being conducted through this little circuit. The light bulb is dim or off, right? In this case, it looks like it's completely off. Versus over here, the light bulb looks like it is lit, which means there is current going through, and that you are able to get electrons or some charged species to be moving around in order to light this light bulb, right? So this is conductive. And if you look at this counterexample, over on the right-hand side, right, they're saying that you have KCl dissolved in this water. And if you look at KCl, right, you have a metal and a non-metal, which means it's an ionic compound. And for us, and we'll kind of review this more in a second, but because it has potassium in it, we know it's water soluble. So it's an ionic compound, it is soluble, which means that it dissociates into ions, right? It dissociates into K pluses and Cl minuses when you dissolve it into water. So that means it does produce those ions that we were talking about, right? We said that in order for water to be conductive, it's got to have ions dissolved in it. And in this case, KCl does form ions, so it does make it conductive. Another way to say this is that ethanol is not an electrolyte, whereas KCl is an electrolyte, right? These compounds, one is a non-electrolyte, one is an electrolyte, and that's based on the fact that KCl gives ions that allows a solution to be conductive. So let's get a little bit more in the weeds here, right? Often you'll hear electrolytes put into place into 3 categories called strong electrolytes, weak electrolytes, and non-electrolytes. For the strong electrolytes, right, these are things that are going to make a solution very conductive. I'll say makes a solution very conductive. right? And the idea is that that's because it's going to dissociate into a lot of ions. A weak solution, well, and let me say this another way, right? If it makes the solution very conductive, the classic test that you see is that it's going to make a bulb burn very brightly. This is in contrast to a weak electrolyte, which only makes the solution a little conductive. Or in other words, a light bulb will burn dimly. Not super bright, not off, but it'll burn just kind of low. It's like when you have a dimmer switch. It's just kind of like a dim glow. And then the last one, right? Non-electrolytes, as you can imagine, right, do not change the conductivity of water. Or in other words, the light bulb will not turn on. And in this case, I'm using a light bulb as an example just because it's a really easy thing to see. But this would be any electrical anything. It could be a motor. It could be whatever. So how do we identify these, right? So the idea is that you want to be able to look at a compound and say, oh, that's probably a strong electrolyte. That's probably a weak electrolyte. And for us, we're not going to get too into the weeds, but I'm going to give you some just general rules of thumb. We already said that strong electrolytes, right, need to produce ions, right? So the idea is that they produce lots of ions. Produce lots of ions. That's kind of the key thing, right? They produce lots of ions. What produces lots of ions? We've already talked about water-soluble ionic compounds. Right, water-soluble ionic compounds. So for us, that was things that, remember we said like started with an alkali metal, so sodium something, lithium something, potassium something, or those really water-solubilizing anions, so like nitrate, acetate, etc., right, perchlorate. The other category that's going to fit in here is those strong acids. Right? There's lots and lots of strong acids, but you should know the 8 strong common ones, right? Hydrochloric, hydrobromic, hydroiodic, sulfuric. Well, let me write them down at the strong acids just to remind us. I know this is in an earlier lecture, but hydrobromic, hydrochloric, hydroiodic, nitric, sulfuric, and perchloric. Right? Because the idea with those strong acids is that they 100% of the time dissociate into, in the case of like hydrobromic acid, 2 ions, H plus and Br minus. So they also will produce ions, right? And remember that an electrolyte is something that produces ions when it's dissolved in water. So strong acids would count as an electrolyte, a strong electrolyte. The weak electrolytes for us, we're not going to get hardcore into like the various solubilities and KSPs of different things yet at this point. For us right now, right, the idea is that we're just looking for things that only produce a few ions. Right, they're only going to produce a few ions. So for us, the big example is going to be the weak acids. And remember, for us, weak acids are going to be things that start with H, but are not one of those 8s. So it's kind of like everything but. Again, there's lots and lots and lots of strong acids out there, and there's varying degrees of weak acids. But for us, if you see an acid and it's not one of those strong ones, then consider it a weak acid. Like for example, phosphoric acid, H3PO4. It starts with an H, so we know it's probably an acid. But it's not one of those 8 that I listed right up above in blue. So it's a weak acid, so that means it dissociates only a little bit. That only some of this is going to separate into H plus and H2PO4 minus 2. It's like we're talking like tens of thousands, you know, one in 10,000, one in 100,000 type of thing. So it only produces a little bit of ions, so the solution only becomes a little conductive. And then for the non-electrolytes, we're going to have, right, no ions, right, does not produce ions. Does not produce ions. So that's going to be our covalent compounds. Right, all of our covalent compounds that are not acids. And that's going to be our insoluble ionic compounds, because if your ionic compound is not soluble, it's not going to produce any ions. So insoluble ionic compounds. And that's how we're going to identify these, right? So strong electrolytes are going to be water-soluble ionic compounds and strong acids. Right, water-soluble ionic compounds and the strong acids. Weak electrolytes are going to be just the weak acids, or in other words, things that start with H that are not those magic 8 ones up there. And then non-electrolytes are going to be our covalent compounds and our insoluble ionic compounds. So let's take a look at some questions involving these. Or actually, sorry, we're not questions yet. Let me touch back on that light bulb situation. So here we are back at the light bulb diagram, right? If I'm taking a look at this, again, so we have ethanol, which you may not know by name. That's totally fine. But if you saw a formula that said like C2H8O, you should say, oh, well, that's covalent. Right? It's all nonmetals. All those things are on the same side of the periodic table, so it's covalent. Also, this is not an acid. So I should be thinking right off the bat that this is a non-electrolyte. And I expect this bulb to not light. Right, which is what you would see. You'd see it, you might see a slight glow, but more or less it would just, it'd look basically off. If I take a look at this second one, I see KCl. So I've got KCl. I know that that's ionic because KCl have a very large difference in electronegativity. And I know it's water soluble because it has potassium in it, right? Because it has that alkali metal. So I know it is water soluble. It is an ionic compound. So I'd say that this is a strong electrolyte. Which is why this light bulb is burning brightly. And then lastly, I have acetic acid. We may not know what acetic acid is, but I see the word acid, and I know acetic acid is not one of those 8, right? It's not the hydrobromic, hydrochloric, hydroiodic, sulfuric, perchloric, or nitric. So it's not one of those, so it must be an acid. And it must be weak, again, because it's not one of those 8. And so therefore, it should be a weak electrolyte. Which means this should burn dimly. This should be dimmer than the other one, right? Assuming that you have the same number of moles of the compounds, you know, in each solution. So that should be the one that burns dimly. And that's what these 3 diagrams are trying to show us here. Now, if we come back to this Gatorade thing, right, when they're talking about like, oh, we've got electrolytes, obviously they're not talking about trying to light up light bulbs or conduct electricity or anything like that, right? They're trying to talk about retaining water, right, which these salts can help retain water. You'll talk about osmosis and stuff like that later. These electrolytes can be really important for a whole bunch of cellular functions where you're pumping in and out these ions. You have calcium-gated channels, all kinds of really important physiological things going on. And again, you lose these in sweat. So if I take a look, you know, I'm putting on my chemistry hat here. I see water. Okay, well, that's just water, no problem. Sugar is C6H6, or sorry, H12O6 generically. All the sugars, these are monosaccharides. I'm just going to show the formula for a generic monosaccharide. But if I look at that, that's covalent. And therefore a non-electrolyte. So that must not be why this is considered an electrolyte solution and why it's going to help you retain water. Dextrose is a fancy name for glucose. It's also a sugar, relatively simple sugar. I see here that we have citric acid. So I know I have an acid. I mean, it says so in the name. I don't know what the formula is of citric acid off the top of my head. Don't worry about it. We don't need to. But if I look at citric acid, I know, again, that it's not one of those 8 strong ones. So I'm going to assume that it's a weak one. And therefore that this is a weak electrolyte. So there's our first electrolyte that we see in here. It's probably the citric acid, right? We've got some citrate and some hydrogen ions in there, right? So those are electrolytes. I see in here salt. When people who aren't chemists say salt, they're almost certainly talking about table salt, which is NaCl, right? Salt for chemists just means any water-soluble ionic compound. So there's thousands of salts. Again, one of the more common ones you've probably heard of is Epsom salt, which has neither sodium nor chloride in it. It's magnesium sulfate. That's Epsom salt, and it's called a salt because it's soluble in water. Here on a food label, it says salt, so talking about NaCl. I know that this is ionic because sodium's on the left, chlorine's on the right, and therefore this is a strong electrolyte. So here's some electrolyte that's in our Gatorade. I look at this, I see sodium citrate. Not 100% sure about that, but I see sodium and something else, so I'm going to assume this is also ionic, also a strong electrolyte. And I'm assuming that it's a strong electrolyte and ionic and everything because it starts with sodium. And I know that sodium-containing things are water-soluble. And I could say the same thing for this one right below, right? It's kind of getting hard to see now, but the monopotassium phosphate, same idea, right? It's got potassium in front. I know that anything with potassium in it is a water-soluble ionic compound, so put that in there. And then we have some food starch and some colorings and flavors and stuff, but we won't go through all of those, all the rest of those. But you can see that I do have some electrolytes in this Gatorade, right? Namely some, it looks like the citric acid is a weak electrolyte, and then we have all of these ions. These would be the electrolytes. And so when you drink something like Gatorade or Powerade or whatever, the idea is that if you had a drink with just these electrolytes in them, it would taste pretty cruddy because it'd be real salty and weird, which is part of the reason why there's so much sugar in these, right? It's mostly water and sugar, tons of sugar in Gatorade, and that's just to make it taste good so that you drink it and so you don't notice how salty your drink is. But again, that's what they mean for, consumer products. In chemistry, it's does it help conduct electricity? So here's just some chemistry-ish type questions, right? We should be able to, and maybe this would be a good time for you to pause, read these 3 questions, and see what you think about them. So in this first question, right, it says, which of the following would be considered a non-electrolyte? And so I should immediately be thinking, oh, well, non-electrolytes for me, those are covalent compounds. So I'm going to get rid of anything that's not a covalent compound. Right here, I'm already looking at D. It just kind of caught my eye. Sodium bromide, that's ionic. So I know that's not it. That's probably a strong electrolyte. HI is a strong acid. That's going to be a strong electrolyte. This thing looks like it's also ionic. Can't be that. And then my first thing is CH3OH. That is covalent. It's not an acid that I know about, so that's going to be my best answer, right? That thing's covalent. It must be a non-electrolyte. It's not going to form ions when it's dissolved. So I would not expect it to light up a light bulb, for example, or motor or whatever. Number 2, a student is conducting the light bulb experiment, like we were talking about, in a solution of 0.09 molar oxalic acid. What should they predict regarding the brightness of the light bulb? So should it not light up? Should it light up a little bit? Or should it light up brightly? And then explain your rationale. So it looks to me like they're putting in oxalic acid. And this is another case, right, where we see that it's an acid, but it's not one of the strong ones. So I'm going to assume that it's weak, right? It's not one of those 8 strongs. So I'm assuming that it's weak. And so my prediction would be that the light bulb should be dim. I'll say should glow dimly. Because oxalic acid is a weak acid and therefore a weak electrolyte. Right, that would be my explanation. It was what I think. I think it's going to be dim because it's a weak electrolyte. Why do I think that? Because oxalic acid is a weak acid. And then lastly, classify each substance as a non-electrolyte, weak electrolyte, strong electrolyte. We would go through these using those same things, right? HBr was one of those strong acids. So therefore, I think it's going to be a strong electrolyte. K2SO4 looks like it's a water-soluble ionic compound. Therefore, it's also going to be a strong electrolyte. HF, it starts with an H, so that looks to me like an acid, but again, it's not one of the 8 strong ones like HBr was. So I'm going to say that's a weak electrolyte. NaF is ionic. It's water soluble. Therefore, strong also, strong electrolyte. CH4, that's covalent. So that should be a non-electrolyte. And then lead iodide, that is an insoluble ionic compound. And that means it also should be a non-electrolyte. It's not going to dissolve in any appreciable amount, and so therefore it's not going to produce ions, so it's not an electrolyte. So anyways, I hope that gives you a better sense of kind of what electrolytes are and then how to identify them. Again, for those weak electrolytes, there's a lot of like squishy middle ground, but for us, we're just going to look at the weak acids that we know of as being those weaks. Strong are all of the strong acids, and the water-soluble ionic compounds, we're following those those solubility rules that we talked about earlier. And then the non-electrolytes are just covalent compounds, and then the things that are the ionic compounds that are not water-soluble. So I hope that gives you a better sense of everything. Happy studying and good luck.